You know, in the world of cryptography, there are tough problems, and then there are legends. For decades, the big one, the real holy grail of the field, was something called Fully Homomorphic Encryption. It's a technology that could literally change our entire relationship with data, and today, we're going to unpack the puzzle, the problem, and the absolutely brilliant breakthrough that finally made it real.
Okay, let me ask you something kind of weird. Imagine you could have a surgeon perform a super complex operation on you, but you stay safely locked inside a completely opaque box the entire time. The surgeon never sees you, never touches you, but can still do their work perfectly. Sounds impossible, right? Well, believe it or not, that's the exact problem cryptographers were trying to solve with our data.
And that impossible surgery? That's the perfect way to think about Fully Homomorphic Encryption, or FHE for short. It's this incredible ability to do any kind of math, run any kind of program, on data while it's still completely locked up and encrypted. It means a cloud server or a data analyst can work with your information without ever having the key to see what's actually inside.
So, why was this such a monumental challenge? I mean, why was it the Holy Grail? To really appreciate the breakthrough, we first have to understand the decades-long, frustrating quest that came before it.
This idea goes all the way back to 1978. But for the next 30 years, 30 years, researchers were basically stuck. They made some progress, sure. They created systems that were partially homomorphic. They could do one thing, like add encrypted numbers together or multiply them, but never both. And to run any kind of useful program, you absolutely need both. The whole package just seemed out of reach until 2009.
The reason everyone wanted this so badly is because the applications are just game-changing. Think about it. You could send a search query to a search engine totally encrypted. It would find your answer and send it back, all without ever knowing what you asked for. Or imagine hospitals being able to pool all their patient data from medical research, finding life-saving cures without a single person's privacy ever being at risk. It completely rewrites the rules of privacy.
So what was the big roadblock? What was the villain of this story? The one technical problem that made FHE seem completely impossible for so long.
So remember those partial systems? They could do one type of operation, like addition, over and over, no problem. But to be fully homomorphic, a system needs to handle both addition and multiplication. You need both to build any meaningful computer program. And it was that combination that was the killer.
And here's why. It all comes down to this one incredibly annoying little problem. In the types of encryption needed for this, every single calculation you perform adds a tiny bit of random mathematical noise. Think of it like a perfect audio recording, and every time you make an edit, you introduce a little bit of static. So you start with a nice, clean, freshly encrypted piece of data. After just one operation, it gets a little bit fuzzy. After a few more, that static, that noise, just builds up and up and up until it completely drowns out the original message. The data just becomes cryptographic garbage. It's totally useless.
And there you have it. That was the 30-year-old puzzle. How on earth do you clean the static out of the recording if you're not allowed to listen to it? How do you refresh a ciphertext to get rid of the noise if, by definition, you can't open the locked box?
And that question, that's what brings us to the climax of the story. This is the moment, the stunningly clever, almost paradoxical solution that finally cracked the whole thing wide open.
The solution is so brilliant it almost sounds like a riddle. To clean the noisy data, you decrypt it. But you do it homomorphically. You basically tell the system to run the decryption program on the data while it's still locked inside its own encrypted box.
Okay, I know, that's a bit of a mind-bender, so let's walk through it. First, you've got your noisy ciphertext. The message M is in there somewhere. Now, separately, you take the secret key needed to decrypt it, and you encrypt that key with a brand new, different key. So now you have two encrypted things, the noisy data and the encrypted key to clean it. You then feed both of these into the system and tell it to run its own decryption function, homomorphically. And what comes out the other side? A brand new, clean ciphertext of the original message, with all that noise wiped away, ready for more computations.
And this is the core concept, straight from the source. Craig Gentry realized that if you could just build a system that was powerful enough to perform its own decryption procedure on itself, you could just repeat that process forever, cleaning the noise after every few steps. As he put it, you just need a scheme that can evaluate its own decryption circuit.
Okay, so having a brilliant, mind-bending idea is one thing, but actually building it is something else entirely. So how did Gentry turn this incredible theory into a system that actually worked? Well, Gentry's first attempt was so close. He built a scheme that was powerful, but its own decryption function was just a tiny bit too complex for it to handle. It was like a mechanic building a revolutionary new engine, but the one wrench he needs to fix it is just one size too big. So he did something genius. He didn't make the wrench bigger, he re-engineered the engine to be simpler. He squashed the decryption circuit, making it just simple enough for his almost good enough system to run on itself, and with that one change, he had a bootstrappable scheme. He'd done it.
So, the code was finally cracked. But what does this breakthrough actually mean for all of us? Let's take a look at the impact and the future that this technology makes possible.
So, you see this number up here, 4,628. What's that about? Well, at the time we're making this, that is the number of other academic papers that have cited Gentry's original 2009 work. In the world of research, that isn't just a big number, that's an earthquake. It shows this wasn't just another small step forward. It was a foundational breakthrough that kicked off an entirely new field of study.
The shift in thinking here is just profound. For most of the internet's history, security has been about protecting secrets, protecting data when it's sitting on a server or moving between 2 points. FHE opens up a totally new world, a world where we don't just share protected secrets, but we can perform shared collaborative work on data that remains completely private to everyone involved forever.
And that leaves us with this final, really powerful question. Now look, this technology is still incredibly complex and computationally expensive for now, but the door is officially open. It forces us to ask, what could we achieve if data privacy was no longer a compromise, but an absolute guarantee? What medical breakthroughs, what financial innovations, what new ideas could we unlock then?